Okay, so this is going to be the first video of Chapter 16, Functions of High Pressure Fuel Systems. We look at some of our different types of fuel systems. This is the distributor pump, which we used for a lot of years as a rotary pump driven by the cam. You had an injector line for each injector coming off of it, so it was a little bit like a distributor for automotive. That's why it's a distributor type pump. The engineer would be working on in the shop has unit injection system, so it's camshaft operated. Works a plunger on the injector, so the camshaft is controlling the injector when it injects fuel, and you don't have a high pressure line or anything. Everything is done inside the injector. That's why it's called a unit injector system. Some of our foreign manufacturers used a UPS or a unit pump system, so it had a little pump over here in the block driven off of the cam, a line coming off going to the injector for that cylinder, so it was still operated by the camshaft, but you did have a line, but you didn't have a distributor type pump. What we use now pretty much exclusively worldwide for emissions reasons and performance is what's called a common rail fuel system. So we have a high pressure pump feeding a common rail. Each injector is controlled by the computer, so our pressure is a lot higher than it is with these other systems. So this is what we'll be covering next week, is the common rail fuel system. Okay, so this is kind of a demonstration of how the fuel works. We got a fuel inlet, a plunger that's going to generate our high pressure, line coming off going to the injector. When the pressure gets high enough, it collapses this spring, opens this nozzle out the valve, and sprays fuel into the cylinder. So this is kind of a little bit of an older slide, I believe, but 32% of our cost of repairing engines is the fuel system. So it's pretty important to know how it works, because we have a lot of issues. 32% of the time our failures, are with the fuel system. Okay, so let's talk about the reason for high pressure fuel systems. Fuel pressure must be higher than compression pressure. Earlier on in engines, we learned that diesel engines have about 425 pounds, somewhere right in there, of compression inside the cylinder. So our fuel system has to be high enough to overcome that. Fuel injection event must happen very quickly, so within milliseconds we have to have all our fuel injected. It's a very fast event, so high pressure makes that possible. Fuel must be atomized upon injection. So atomized is a really fine spray. You can take diesel fuel, and if you were trying to start a fire to burn some brush or something, you would find that you can't get the fuel to really ignite unless you have like some paper or something like that burning to get the fuel started. Then it will burn. It's not like gasoline, where if you tried to start a fire with gasoline, you could get burned or because of an explosion or something. So diesel's a little harder to get on fire. When fuel is atomized, though, I've seen some old videos which are very dangerous, and nobody should do that, but with a pop tester where they pressurize an injector and to get it to pop open and spray, they could take a cigarette lighter and it's like a flamethrower. There's a very large flame front coming out when fuel's atomized under high pressure. Back to our fuel pressure must be higher than compression pressure. That air is extremely dense at the end of the compression stroke, so it takes a really high fuel pressure to force fuel into and around and mix with all the air molecules to get proper ignition. So that's why we have to have a very high pressure. There's our atomized fuel. It's tiny little droplets, very fine mist. When I said it's high pressure, our range about 4,500 psi to up to 37,000 psi on common rail. So really have to be careful with that, because 37,000 psi will inject diesel fuel into your skin, and you could actually die from that. So a lot of safety precautions when it comes to the common rail. We'll get to that next week. So let's talk about our fundamentals of high pressure fuel systems. Functions of the high pressure fuel system: we have to meter the correct quantity of fuel for injection. Remember, on a diesel engine, we don't regulate how much air goes into the engine like gasoline with the throttle plate. We put the right amount of fuel to get the speed that we want. So we have to meter the correct quantity of fuel with our fuel system. We have to time injection of the fuel, control the rate of fuel delivery, so how much and how long the injector is on. We have to atomize the fuel and distribute fuel throughout the combustion chamber. So one of the things that makes diesel more efficient, our fuel is sprayed and our nozzles are angled to where that we get the fuel throughout the combustion process and don't have to, allow it to mix. It sprays in all directions and has a more complete burn to get more out of the fuel and less waste. Fuel metering measures and delivers the correct quantity of fuel for each cylinder for the current load and speed conditions, and we have to be able to change this as engine loads and speeds change. So we need more fuel if we put more load on it, so we have to be able to do all this with our fuel system. Fuel metering, we also want our fuel to give us a high combustion, but more importantly, we want our timing to be where that we're about 10 to 15 degrees after top dead center when we have our peak combustion pressure in the cylinder. That gives us leverage here. If it fired when it was straight up and down, we wouldn't get as much out of our explosion. We want this offset here to be leverage to multiply what our force on top of the piston is. So back when we had mechanical injection, we had this injection pump, so it had flyweights here in the back to control speed. As it got the turning too fast, the flyweights would pull the fuel back and control the engine speed, so that was the governor part of it. It controlled everything from low idle to high idle, so 650 RPM to 3,000 or whatever this engine would operate at. So our throttle linkage went to the governor, and that's how we told it how fast we wanted it to run. So, and then this was our high pressure pump part of it here, so the governor was controlling the pump. Now everything's electronic, so just to fire this injector, the computer has to have all these inputs: a cam sensor, throttle position, turbo boost pressure, crank sensor, fuel pressure, fuel temperature, oil pressure, oil temperature, air inlet temperature, coolant temperature, and coolant level. So one might think, well, what's coolant level have to do with the injector? Well, if I'm low on coolant, I may have a safety feature on the vehicle that won't let the injectors fire, so it won't let it start because the coolant level is low. The computer can monitor coolant temperature, so if the engine starts getting too warm, it can cut the fuel back, not necessarily shut the engine down, but keep the driver from burning the engine up. Air inlet temperature is going to tell it the density of the air. Oil temperature, same thing. If the oil temperature is going too high, it could damage the engine, so it may cut the fuel back and run under reduced power. Oil pressure lets it know if the engine's running or not, or if the oil pressure gets too low. Once again, I can shut the engine down. Fuel temperature, that's going to affect combustion, so the computer needs to know that. What the fuel pressure is, crankshaft sensor, turbo boost. So all these things go into making this engine run. So it's a lot more complex than it used to be. Related to the fuel system, get the pulse out to the injector. When it wants that injector to fire, it gets feedback from it as to how long it was on. I have a diagnostic connector, and I have warning lamps. So all these are outputs out of the ECM. So how fast the engine's running or turning, how warm it is, what load it's under, all these things can be the inputs that the ECM needs. Electronic metering control benefits: increased fuel economy. We have the ability to get a lot better fuel economy out of the diesels now than we used to. Reduced emissions is what's really driving it with the EPA, because if I can better control the fuel and the burn, then I'm going to have less bad emissions out the tailpipe. More power. We can make a whole lot more power with the diesel engine now than we used to with this electronic stuff. Prime example of that would be about 1988, the 7.3 IDI diesel came out in the Ford, and it was 165 horsepower, and everybody thought it was a great engine for a truck and so superior. But today's 6.7 Scorpion Ford engine is actually smaller, 6.7 liter instead of 7.3, but instead of 185 horsepower, it's at 385 horsepower. So smaller engine, but with the fuel systems we have now, with the more advanced turbos and stuff, a whole lot more power. And the engines are quieter now because I can tailor the fuel injection to 5 to 7 injection events during one cycle. And that's what makes them a lot quieter, more reliable. When everything's working right, it's a lot more reliable, and longer service intervals, so I don't have to do some of the services on the vehicles near as often, because I can more efficiently burn the fuel, not have excess fuel and things getting past the rings into the engine. So there's algorithms in the software that basically can tailor the optimum fuel metering and timing for the current operating conditions. That's why they run so much better and more fuel economy and stuff now. So luckily we don't have to get into all this because we're not engineers, but lookup tables to store the data. It's crazy to see the breakdown of what a computer does just to control the fuel system. A few more things: metering and torque control. Diesel engines don't have throttle plates like we discussed earlier, so no pumping loss as a result. That's one of the problems with the gasoline engine that hurts them, is the intake's running under a vacuum and you have a pumping loss to it. You don't have that with diesel because we run on excess air, so there is more air than we need to burn the fuel. Gas engines have this problem because they're trying to draw air in under a vacuum, so they're trying to tailor the air to control the engine speed, so you lose a little bit there. Hunting on the diesel engine, we used to have a lot of problems with this back in the old Governor days. If they weren't right, but at an idle, they would kind of speed up and slow down and speed up and slow down. That was called hunting. We don't really have that problem now. And like if you came down to an idle, the RPMs would go lower than they needed to and come back. So on the older diesel engines, it was a little different than what it is now. Metering and idle adaptation. Cylinder power variations can be caused by various factors, so getting uneven fuel quantity, delivery from cylinder to cylinder, or mechanical problems, one or more cylinders. That can give me some metering problems, but idle adaptation is what we use on modern engines. So with that, if I have a cylinder that's not doing its job and the RPMs are a little low, when that cylinder fires, the computer will kick in and give the cylinder that fires before that one and afterward a little more, so that it smooths it out, so that you don't have like a rough running engine at idle, but it also tracks that and will set a trouble code for it. So I'm going to shut it off for this video, and we'll pick back up on video 2.